I thank IMPA for its hospitality and very generous support. And I thank Enrique for all the work he did and his very warm reception here. What do I want to do? Well, I don't want to study Poisson structures on manifolds or even on the algebroids, because you all know all about it. Do I want to study Poisson pairs, which are also called bi-Hamiltonian structures? Well, that was done also, dating back to the first paper of Magritte, unpublished paper of Magritte and Morosi, my own work with Magritte, and many, many others. But what I want to do today is to study pairs of compatible Poisson structures and other various compatible structures on the algebroids, also, I hope, on Courant algebroids, and that with different methods, and give new examples. So what will I be talking about? Well, the usual, the basic tools that I need to use, which I will recall as briefly as possible. And then I will give a survey of what you can consider as a zoo of various compatible structures on the algebroids. And that will be followed by examples that come from the theory of Monge pair operators. And that part is basically the work of Volodya Rubtsov. And we have a paper in common where that is explained. And then I would like to say a few words about Dirac pairs. What basic tools do I need? Well, I need the bi-graded Poisson algebra, which is denoted here by f of v. So what is it? We have a vector bundle, v over manifold M. Everything is smooth. And we can consider the graded manifold, which we obtain from this vector bundle by assigning degree 0 to the coordinates on the base, degree 1 to the coordinates on the fiber. And then we consider the cotangent bundle, T star of V, but with the grading indicated by the T star 2 of V1. And it's very easy to use local coordinates, and here are the by degrees, xi's of the coordinates on the base, xi on the fiber, and pi and theta a of the associated momenta. Now, because we're dealing with a cotangent bundle of a graded manifold, it comes equipped with a canonical even Poisson structure, even symplectic structure, and therefore an even Poisson bracket on this algebra of functions. This is the work of Reutenberg, of Dmitry Reutenberg. This bracket, this Poisson bracket on f of v, I call the big bracket. Why do I call it the big bracket? Well, you remember that it appears in the theory of Lie bialgebras already in a special case when instead of a vector bundle we have a vector space. And here is the a little bibliography on this subject. And in this paper in 1992, I used it to define the bicomplex of a Lie bialgebra, introduce proto-bialgebras and quasi-Poisson Lie groups. So this is the big bracket that I will be using on and on. And I can already announce that I didn't write any proofs, or maybe just one in the file. Each proof is use the graded Jacobi identity as many times as necessary. So here are the properties of a big bracket. Its by degree is -1, It is Q-symmetric in the graded sense, and it satisfies the graded Jacobi identity. And in local coordinates, what does it look like? Well, if you take a coordinate at its momenta, the Poisson bracket is the delta, the Kronecker delta. This being said, I will also be talking about or introducing derived brackets. Well, derived brackets can be defined the construction can be carried out on any graded Lie algebra equal to the not derivation of square 0. And that yields not a novel Lie algebra in general, but a Laudet Leibniz algebra. Here I present this construction in the particular case where the derivation of square 0 is interior derivation by an element small d in a graded Lie algebra A. And it's the derived bracket is defined as simply as possible. You take two elements in A, small a and small b, and you declare the derived bracket to be the original bracket of A and D, the whole thing bracketed with B. And what's the result of doing that? Well, you get something which is, in general, non-skew symmetric, but it does define the Jacobi identity in the way you want it to satisfy, or in the most convenient way, which is by saying that taking bracket by an element is a derivation of the algebra. And what's important in practice is that if you restrict such a Laudet-Leibniz bracket obtained by the construction of derived brackets, then if you restrict such a derived bracket to an abelian subalgebra, in the abelian with respect to the original bracket, and this subalgebra you assume to be invariant under taking a bracket with your derivation d, then what you get is a Lie bracket. So you have a construction, a graded Lie bracket. You have a construction that leads from odd Lie brackets to even Lie brackets, or vice versa, depending on where you start from. And now you all know what a Lie algebroid is, but I'm going to tell you what I think a Lie algebroid is, or what Dmitry thinks it is. Well, it's a vector bundle. Call it A basis with base M, and it's equipped to an element of by degree 1, 2, which is here denoted by mu, in this big algebra of functions on the cotangent of A, and it has to satisfy bracket mu mu equals 0 with respect to the big bracket. So this corresponds to the notion of a cohomological vector field that Alberto Cattaneo was talking about last week. So if we start from such a mu, well, we can reconstruct the familiar objects that live on Lie algebroids. The anchor, the bracket. Notice that each is defined by a derived bracket. You see x mu f, you see x mu y. And more generally, you have a very compact formula for this Houghton-Einers bracket of multivectors. I call vectors sections of A, forms sections of A star, etc. And of course, once you have defined this anchor and this Lie bracket, you can verify that because of a property bracket mu mu equals 0, you get all the usual properties in the definition of a Lie algebroid. So you also get the fact that you have a Gerstenhaber algebra structure on the sections of the exterior algebra of A, and you have all the familiar examples. An important example is when the base is just a point, and then it's just a Lie algebra. When the vector bundle is a tangent bundle of a manifold, then you generalize the Lie bracket of vector fields, etc. And then associated to Poisson manifolds, you have the Lie algebroid structure of a cotangent bundle. You have Lie algebroids defined by a group acting on a manifold, or an infinitesimal Lie algebra action. You have Lie algebroids associated to foliations, etc., etc. And given a Lie algebroid, what is the Lie algebroid cohomology operator in this formalism? Well, it is very simple. It is taking bracket with a structure. Mu is the structure defining the Lie algebroid, and bracket with mu is the Lie algebroid differential. So this reduces to Chevalier-Eilenberg cohomology in the special case of a Lie algebra over a point, and to the Ram cohomology. And also the Lichner-Horowitz-Poisson cohomology operator is of this form. Lie bialgebroids, they generalize Lie bialgebras in the algebroid framework, and they're defined in a very simple way, just by taking a bracket and a co-bracket, an element mu and an element gamma of suitable bidegrees, and writing that the sum squares to 0. Another alternative way of defining these objects is to look at the Gerson-Haber algebra over A, defined by mu, and together with the differential d gamma defined by the co-algebroid structure, you have to have a differential Gerson-Haber algebra. That means that d gamma has to be a derivation of a bracket, of a Gerson-Haber bracket mu. Here you have a very boring list of what else you can do. Once you have mu and gamma, you can look at more generally what's the most general element of total degree 3 that you can consider. And of course, you can have a 3 tensor called phi. You can have a 3 form called psi, or you can have both. So in one case it's quasi-Lie, in the other case it's Lie quasi, and then finally you introduce proto and you have everybody. So the examples are, first of all, in the Lie bialgebras and their generalizations. And also an important example comes from the consideration of Poisson structures with a free-form background, sometimes called twisted Poisson structures. Now, I want to convince you that the big bracket is good for everything. So if we have a bivector, a section of wedge 2 of A, then it maps A star to A, and the way to express how it acts on forms is just to take the bracket, the big bracket of pi with alpha. Same thing for a 2 form. Well, there is a change in the order of things, but that's normal. There are signs all over the place, but if you do it carefully, there are not too many signs that appear. And if you have a 1-1 tensor, and you want to apply it to a section of A, what do? You take big bracket, and you get the answer. And also, if you have a bivector and a 2 form, then that defines a map from A, an endomorphism of A, and that's just the big bracket of pi with omega. Very simple. What is a Poisson structure on a Lie algebroid? Well, it's what you expect. It's a bivector that has Schouten bracket with itself 0. But if you are interested in the theory of algebroids and the big bracket, you do the following. From your bivector, you're going to construct a candidate for being a Lie bracket on the dual, and that's the gamma pi over there. And then you are going to ask, under what conditions is that going to be a Lie algebroid structure on A star? And that's given by this condition, which by the Jacobi identity and the definition of a Schouten bracket as a derived bracket, you can see immediately is equivalent to the condition here, which says that pi pi mu is a d-mu cycle. And you find this sufficient condition that it be a Poisson bivector. So a Poisson structure is defined by a Poisson bivector, and in particular, it defines a Lie algebroid structure on the dual of A. Okay, if you extend this bracket of one forms to forms of all degrees, it's called the Kosul bracket, and it was introduced by Kosul in his paper in 1985, I think. If you want to deform a Lie algebroid structure, you will need an endomorphism of A. So let n be a 1-1 tensor on A, and then you consider this expression. This is a new candidate for being a Lie algebraic structure on the same vector bundle A. And so we call it the deformed structure, or it is also called the contracted structure. And once you have decided to look at this, you associate with it an anchor and a bracket, which is defined by this formula. And when you expand this, knowing how you to compute with the big bracket, you see that it is given by this formula, which is the usual deformed bracket. Now you want to know when the preceding bracket is going to be a Lie bracket again. So you introduce the Nionist torsion of n. That's the Fröhlichen Nionist, 1/2 the Fröhlichen Nionist bracket of n with itself. And it's by definition given by this formula. And if you rewrite it, you immediately see that it's the difference. Well, it measures the defect of being a morphism of Lie algebras. Now, the formula below tells you how to look at the torsion in terms of a big bracket. And that's very useful if you want to do everything using the big bracket. So this formula is due to Grabowski. I also found a proto-formula in one of my old papers.
But n squared is not, I mean, it uses n and n squared, not just n.
Yes, it has n squared. You can't get rid of n squared. So that's why complex structures are almost complex structures and almost product structures are so nice, because then you get the identity and everything is much simpler. But you do have an n square there. Yes, I was going to explain what's a complex structure, but you know, and you can play the game again of asking when is this deformed structure and you're going to be a Lie algebraic structure. And again, it's very similar to what you had for Poisson structures. A sufficient condition is that the torsion be a cocycle, and therefore, a necessary and sufficient condition is that it be a cocycle, and for a sufficient condition is that the torsion vanish. And so down here you have this very compact way of characterizing complex structures. Okay, I said I would speak about Poisson pairs, and I have been talking too long about preliminaries. So what kind of Poisson pairs what kind of compatible structures, bistructures do I want to consider? Well, the ones that are very important for integrable systems. These are the bi-Hamiltonian structures, mostly on infinite dimensional manifolds, but I'm talking here about the finite dimensional case. And also PN structures. So what's a PN structure? Well, you start from an Ionist structure and a Poisson structure on a Lie algebroid, which I denote again by A mu. But then you want the two things to be a pair, in some sense, to be compatible. So you introduce a condition. So here is the condition. Pi bracketed with n mu plus n bracketed with pi mu, that has to be 0. So what does it mean? Well, it means something geometrical, if you want. You start by deforming the original bracket mu by the 1/1 tensor n, and then from that new Lie algebraic structure on A, you twist by pi. Or you can start from the twisted, from the structure on A star defined by the vector pi, and then you deform it not exactly by n, but by its transpose. And in big brackets, the first procedure gives you this expression, the second gives you this one, and taking care of the signs, they're equivalent to the compatibility condition I introduced. So that's what it means. And you can also start asking, what's the relationship with Lieb algebroid? Well, it's very simple. To have a Lieb algebroid defined by this mu n and this gamma pi, you want their sum to square to 0 in the big bracket. And since mu n, if you assume n to be 9 Hertz, then you already have this equals 0, pi is Poisson, this is 0, therefore what remains is the compatibility here. And of course, you again have a statement in terms of necessary and sufficient condition is that something be a cocycle. That's the compatibility expression, be a cocycle. And the sufficient condition is that this expression vanish. So in the case of what I call the PN structure, that's when the compatibility condition is satisfied, then we get a bialgebroid. And the converse is true the additional assumptions. Poisson pairs in the title, what are they? Well, I said it already a number of times. They are a pair of Poisson structures which we assume to be compatible in the sense that their sum be a Poisson structure. And that's a non-trivial condition, of course. So in the theory of integrable systems, they're usually called bi-Hamiltonian structures. And so the condition for the compatibility, so this is the condition for the sum to be a Poisson structure. And so the whole definition is equivalent to pi Poisson, pi 1 Poisson, and then compatibility in the middle. So what can you do with a PN structure? Why is it nice to have a PN structure? I mean, I want you to be convinced somehow that these things are good for something. Well, you can have a hierarchy of Poisson structures starting from your pi equals pi 0, pi 1, and then pi 1 is n composed with pi. So how do you get pi 2, pi 3? Well, you take powers of n, and you compose with pi. And these are all structures of the dual vector bundle. And the theorem is that all these pi k are all pairwise compatible. And of course, if, well, the first thing that you have to prove is that when you have a Poisson pair, okay, sorry, I wrote here, but I didn't say that if you want things to work, if you want to have a PN structure out of a Poisson pair, you somehow have to be able to build that 9 Hertz tensor or future 9 Hertz tensor. And that's done by composing one of them with the inverse of the other. So you have to assume that one of them is non-degenerate. And then everything works fine. The resulting 1-1 tensor has 9 Hertz torsion 0, and each pi n and pi 1n is a PN structure. So in this context, this endomorphism of a tangent bundle is called a recursion operator. Oh, let's skip. That's not. That was not supposed to be there. Sorry. Okay, and then you have another statement, kind of converse of a preceding statement. Now, I can go on and on, but I cannot, in effect, go on and on. So I will not say too much about pure omega structure. That's Poisson and presymplectic. And so you can look at the notation. I will have a summary where you can have more information. Here's the definition of P omega structures. So it's a Poisson bivector, and then you have a two form which is closed. That's omega. So you start from a pi and an omega, but then you want a compatibility condition, and the compatibility condition is expressed by the fact that if you define n by combining your pi with your omega, and then you define a new 2 form by combining it with this n, then this new 2 form has to be closed also. This is the compatibility. And, okay, so it's a nice structure, and in terms of the big bracket, you have 3 relations in the definition, and okay, this is just a lemma or proposition, but then you want to know how is that related to what we had 3 minutes ago about PN structures. Well, the answer is that yes, it works. In one direction it works always, and in the other direction it works under a non-degeneracy condition. There's another definition in the literature, more specifically in a paper by Yvette Kosmann-Schwarzbach. That's the notion of complementary 2 form for Poisson structures. So I try to explain what they are in my language, although it's explained very well in Izu's language. So what do? We start from a Lie algebroid. We have a bivector, and we construct this co-bracket. And we know that the condition for this co-bracket to be a Lie algebroid structure on A star is this co-cycle condition. But now we can start from A star with some co-bracket gamma and take a bivector on A star. That's a 2 form on A, right? So we take an omega, which is a 2 form on A, and we do the preceding construction, replacing mu by gamma and pi by omega. And then we have this condition for the result to be a Lie algebroid structure. Now, if I do first the procedure that involves the pi, then the procedure that involves the omega, when in the intermediate step I decide to take the gamma that was defined by the pi, then I get a mu tilde, which is again on A. And then I can ask, when is this mu tilde going to be a Lie algebroid structure? There must be a condition someplace. So an answer is that if we define complementary 2 forms by the condition that omega Schouten bracket of the 2 form omega with respect to the Lie algebroid structure on A star defined by pi be 0, then we call this 2 form a complementary 2 form for pi. And then the proposition is that to be a complementary 2 form for pi is sufficient for the mu tilde to be a new Lie algebroid structure. Okay, you can go on. You can have an explicit expression for this bracket defined by mu tilde, and you. Oh, okay. And if the complementary 2 form happens to be closed, then it follows that the n that you obtain by combining the pi with the omega again has vanishing line distortion. And of course, this is related to p omega structures. So omega n structures, well, you have all guessed. You have an omega, you have an n, and a compatibility condition. And they're related. And also, another thing that is in the literature, although it's in an unpublished paper by Marius Kreinig, is the notion of Hitchin pair. So what's a Hitchin pair? Well, you start from a non-degenerate 2 form and a 1-1 tensor, not necessarily 9 Heuss, and you impose that the omega n, which we defined before, be closed. And of course, if you ask how is it related to the preceding structures which I considered, well, if you're if you start from an omega n structure, then you immediately get a Hitchin pair, provided your two-form is non-degenerate. And conversely, if you start from a Hitchin pair, but you assume that the torsion of n vanishes, then you are in the case of an omega n structure. They have, Hitchin pairs have a distinguished element, which is called the twist, which is defined up there. And there is a nice formula that relates the twist to the torsion of the associated, of the 1-1 tensor n, defining the Hitchin pair. And that's given by this formula, where tau is now the inverse of the two-form omega. It's the bivector which you obtain by inverting the non-degenerate two-form omega. And then there is a generalized complex structure associated to a Hitchin pair, provided there's an algebraic condition, but I was going to speak about that later because I haven't spoken about generalized complex. So I will just let you look at this beautiful table. You have the various things I've been speaking about, and the definitions are summarized, all in terms of a big bracket. And so it's exactly what I showed before. And then the various theorems that I've been stating, or propositions, are summarized in this table, which tell you how P omega is related with Pn, etc. And I can even summarize most of this in just a diagram that tells you what implies what, that these are the solid arrows, and what implies that under some non-degeneracy condition. Okay, I was going to speak about generalized complex structures, but I will move on to examples of such pairs of compatible structures arising from the theory of Monge-Ampère operators. So no courant. And here are Monge-Ampère. Monge-Ampère structures on manifold are defined in the following way, and I refer to the book by Volodya Rubtsov, Kushner, and Valentin Lichagin, which has everything on Monge-Ampère and many, many examples of equations obtained in this way, and many applications, which I'm not going to repeat here, of course. So if M is a manifold, we're still in the C infinity category. Let's call its dimension n, and let's consider its cotangent bundle, which is of dimension 2n. T star M has a canonical symplectic two-form, which is here denoted by capital omega. And a Monge-Ampère structure on M is by definition an n-form small omega on the cotangent bundle, such that its wedge product with the canonical two-form, symplectic two-form be 0. This definition is equivalent to this one, which in which pi sub omega denotes the bivector inverse of a canonical two-form omega. And more generally, a form of arbitrary degree satisfying such a condition is called effective. So we can rephrase the definition of Monge-Ampère structures by saying that it's defined by an effective n-form where n on T star M, where M is a manifold of dimension n. Once we have a Monge-Ampère structure, we have a Monge-Ampère operator defined by this formula. It maps, it's an operator on functions on the manifold, on the base manifold, and the Monge-Ampère equation is delta omega of f equals 0, where delta omega of f is defined by this equation. Now you can ask, why is this called the Monge-Ampère equation by all means? Well, the Monge-Ampère equation is RT minus S2 equals some function defined on R2, real valued function on R2, and RT and S are the second order partial derivatives of some function f on R2. So how are these things related? Well, to justify at least a little bit the definition, I just compute on R2, I take coordinates x, y, p, q, I take a function f, and p and q are the first partial derivatives, and I consider the two-form omega equals dp exterior dq minus f dx exterior dy. I claim it's effective because I immediately check that its wedge with the canonical two-form is 0, and then I compute the definition df pullback of omega by df, and I find this expression. So setting that equals 0 is just the classical Monge-Ampère equation. So what is studied under the name of Monge-Ampère structures is a vast generalization of a classical one. So how is this at all related to compatible structures? Well, you have again to define a few elements, a few notions. So if we, I will look at the case of Monge-Ampère structures on manifolds of dimension 2. So the compatible structures we're going to discover are on a manifold of dimension 4, actually. In fact, the cotangent bundle of a manifold of dimension 2. So because we are in dimension 2, if I omega wedge omega is proportional to small omega wedge small omega, and there is a function called the Pfaffian satisfying this equation, then I can define a 1-1 tensor. Everything is on T star M now, so n omega is a tensor on a 1-1 tensor on T star M defined by this formula, and then you can prove that it squares to a multiple of the identity, and this multiple of the identity is minus the Pfaffian defined by this formula. And the case that I will need will be the non-degenerate case where the Pfaffian doesn't vanish. So if the Pfaffian doesn't vanish, we can normalize the form omega and the endomorphism n omega by dividing by the square root of the absolute value of the Pfaffian. And in that case, then we are reduced to a 1-1 tensor n tilde omega, whose square is 1, so either 1 or minus 1. So minus 1 is the elliptic case, and 1 is the hyperbolic case. So we already have an almost complex or an almost product structure on T star M. So in the book by Kushner, Lichagin, and Rupsov, it is shown that the vanishing of a Ninus torsion of this normalized 1-1 tensor, almost complex structure, or almost product structure, until the omega vanishes. That's equivalent to the two-form omega tilde, the normalized two-form, being closed. And then you nearly immediately get the following list of examples of structures, of pairs of structures. If we're in the case of a non-degenerate Monge-Ampère structure on a manifold of dimension 2, such that in addition the two-form omega tilde is closed, then we get this list of examples: Pn structure, Pn structure, P omega structure, omega n structure. the compatibility conditions are automatically satisfied. Well, it's interesting to note that in a certain case we can prove that by deforming the standard structure of T star m by this normalized endomorphism n tilde omega, the result of that deformation is a Lie algebraic structure on T star m, which happens to be unimodular. So I listed that here. And we can find, again, another case. If we now assume that omega is closed, and we're still on a two-dimensional manifold, and the Monge-Ampère structure is non-degenerate, Pfaffian does not vanish, then considering the canonical two-form, capital omega, with the non-normalized tensor n omega, gives a Hitchin pair. But if in addition we assume omega tilde to be closed, then the torsion of n omega vanishes, and we are in the omega n structure case. Okay, I did not speak about generalized complex structures, but I assume that this was already defined in previous lectures. So what I want to show is how such generalized complex structures and generalized product structures arise again in this theory of Monge-Ampère structures. So first of all, on two-dimensional manifolds, I have the expression of divergence type. So here on this previous transparency, I defined the condition that a Monge-Ampère structure be called of divergence type. That is the situation where the small omega defining the structure and the capital omega, which is the canonical two-form symplectic structure on T star m, you require that there exists a function phi such that small omega plus phi capital omega be closed. And if that's the case, then you can find a beautiful, you can find a generalized almost complex structure on T star m, which was built in the following way. Here it's written in matrix form. So the endomorphism part is n omega and minus n star omega. But you have the bivector part, and then you have a two-form part. And then if omega tilde is closed, this thing simplifies to either this structure in the elliptic case or that structure in the hyperbolic case. And they become generalized complex. So that was on two-dimensional manifolds. Now, what happens on three-dimensional manifolds? Well, given a closed free form on T star m, you first consider the standard Courant algebroid of T star m, which is T of T star m plus T star of T star m, equipped with either the Courant bracket or the non-skew symmetric bracket, which I call the Dorfman bracket. But then, because you are in the presence of a free form, you can twist that standard Courant algebroid structure of T star m plus T star of T star m by the a free form omega, which is then called a background free form, to obtain a new courant algebraic structure. This was explained in the paper of Pavel Shevera and Alan Weinstein in 2001. And then I want to show that there are generalized complex structures associated to this, on this twisted courant algebroid. For that, again, I need a definition or two. If we are on a three-dimensional manifold, we can define an endomorphism. If M is three-dimensional, then T star M is six-dimensional, and on T of T star M, we can define an endomorphism by requiring that for a section of T of T star M, a vector field on T star M, H sub omega of x be Ix omega wedge omega. So this becomes, omega is now a 3 form, this is a 2 form, this is a 5 form, and that's the same as a vector if you use the Liouville volume form defined by the canonical symplectic structure. So this is an endomorphism, which is called the Hitchin endomorphism, and one can prove that given a closed effective free form on R3, then the square of this endomorphism is again proportional to the identity with a factor which is called here lambda omega, which is called a generalized Pfaffian. So what happens in the case where lambda omega is plus or minus 1? Well, in this case, you obtain a generalized either complex in the case lambda omega equals minus 1, or product in the case lambda omega equals plus 1 structure on the twisted courant algebroid which I described, which is the standard twisted by the background of form omega, free form omega. Now there are also some very interesting structures which I did not describe, which are generalizations of Poisson-Nijenhuis. So there was first Poisson quasi-Nijenhuis, discovered by Mathieu Sienot and Ping Su, and then Antunes generalized this further to the case of Poisson quasi-Nijenhuis with background. So you have you have more elements defining the structure. You have some bivector. You have some 1-1 tensor. Then you have a 3-vector, I guess, and then a free form. And associated to such a generalized complex or product structure, Antunes has shown that you get a Poisson quasi-Nijenhuis structure with background of a particular type, because you see you have a 0 here. So it's not quite the general case. It can be called a Poisson-Nijenhuis structure with background. It's not quasi, but it has background. To end the talk, I would like to say a few words about Dirac pairs. We've been talking about Poisson pairs, and we should be talking about Dirac pairs. So if we have a courant algebroid, we know that a subbundle is called the Dirac subbundle if it is maximal isotropic and if it's closed under the bracket. I do not specify bracket. A courant bracket, Dorfman bracket, they're reduced to the same thing. So if we now consider so I would like to define Dirac pairs, and I have not invented the notion. If you look at the book by Irene Dorfman, or if you go further back to the papers of Gelfand and Dorfman in the 80s, you will find this notion of Nijenhuis relation and Dirac pairs. So here I reformulated in terms of Lie algebroids, whereas in their original work it's formulated in more algebraic terms, in terms of complexes. But here is the definition. So we're going to replace Nijhuis tensors by Nijhuis relations in a way. So this is the definition of a Nijhuis relation. And why is it the definition of Nijhuis relation? Well, because a vector bundle morphism is a Nijhuis tensor if and only if its graph considered as a relation in A plus A star is a Nijhuis relation. So this is a definition. So here there is a notation for there's a notation for n star, and for something sub 1. N star is the dual relation of n, and given a relation n, you define this. This is a kind of compatible pairs of a relation. So what are Dirac pairs? Well, Dirac pairs must be pairs of Dirac structures such that if you compose, so if you call them L and L prime, and if you compose L prime with the inverse relation of L, and that always exists, what you obtain is a Nijhuis relation. And of course, this is the basic definition, but here we're using composition of relations, and we heard yesterday morning that one has to be extremely careful about composing relations, and it can be a very difficult subject. So I strongly believe that before you give a good definition of Dirac pairs, you have to add some sort of condition that will ensure that the composition is a sub-bundle. But certainly, formally things work beautifully. If you take Poisson structures and if they constitute a Poisson pair, then their graphs constitute a Dirac pair. If you take a Poisson structure and a pre-symplectic structure, that's a two-form. That's a closed two-form. They constitute a P omega structure, and if they constitute a P omega structure, then their graphs constitute a Dirac pair. So I believe my time is more or less up. Okay, so I will just flash a few questions, because especially these last two slides were just a little bit tentative. Examples: work on Lie-Reinhardt algebras, transpose all that to a purely algebraic framework, and in the case of Courant algebroids, transpose to the Courant-Dorfman algebras that Dmitry Reutenberg defined rather recently, well, 2 years ago. And also, what I think is a worthwhile question is relate Dirac pairs to the Dirac Nijhuis structures that Kariniena, Grabowski, and Marmo introduced back in 2004. I would like to call them DN structures, so we have one more in the zoo. In particular, if I have a Dirac pair in a suitable sense, and then I consider the pair L prime composed with the inverse of L, is that going to be a DN structure? Okay, question, etc., etc. So my time is up. Here are some references, and there are many more, and I apologize for those of you whom I did not cite.